For us,
So good to see you, Ramesh.
Hi. Oh man, you have lockdown has affected you a lot, I see.
Yeah,
Just
that's right.
Manipur, oh, good place actually. I wish I could visit sometime.
Yeah, sure. Come by anytime.
Yeah, let this COVID is go.
Good
It's
morning.
a central university, right?
Ah, yes, it is.
I think one of is this Manipur, if I'm not mistaken. What is her name? I know her sometime. I can't just recollect. Who all are your colleagues? How many of you are there?
So some of my senior colleagues they mostly work on this material science and condensed matter physics.
Mm-hmm.
One is Sumitra Fanjaubam.
Mm.
She works on magnetic properties, experimentalist. Then one is Doran. He works on what is that? Luminescence properties.
Mm-hmm.
Then there is Basanta Kumar Sharma. He works on thin films. Then there is Nimai. He works on high energy physics. Then Yugindro. He works on astronomy and astrophysics. Then I have a new colleague. Her name is Chandra Chini. She works on cosmology.
I see.
And then I am the other person. Oh, there is another one, Nomita. She works on, again, material science. So at present, there are 8 of us in the department, and then 5 guest faculties.
Faculty.
That's right.
Wonderful. Okay. Now, what is this new institute which is coming for Banudas becoming director designate? I've just not heard about that.
I guess Viju can tell you more about it.
yeah, so this is called TCG, Chatterjee, that some group, it's actually he is also funding in US, California. He has several institutes there also. So this one he has started in Calcutta. So it's a private organization right now. Earlier, for last 1 year, this former director of TIFR, Bhattacharya, he was the director. Now he is moving to Ashoka University, and Professor Das will be taking care of he will take off this one.
So is he going to come back, or he is going to work on a...
He has already accepted. He is joining in May. So actually he got 1 year extension in Japan. Otherwise he should have come back. So he got 1 year extension in Japan. So there the retirement age 65. So he got up to 66. So he's joining. Then he'll come back. So he has already joined here.
Oh, he also joined.
Yeah.
Good morning, Manu. By the way, when is his birthday? Is it over or is coming? Or
on 27 June.
You are muted, Professor Das. You are muted. We cannot hear you.
I'm sorry.
Yes. Good morning.
Good morning, sir. After a long time.
Yeah. I mean, the first time since.
Very nice to see you.
Yes, I mean, I'm in the office after 6 months because today is the first day of a new quarter. So I just came to find out a few things that I have to do for this semester. And so everybody is required to wear masks and so on. So that's why my mask is on. So
we are also, but in the room when we sit, we normally, because there's nobody else, so we
I think I mean because here anyone can come anytime. I guess I can just sort of.
So it's wonderful. Let me first wish you many happy returns of the day. But though it is slightly late.
Yeah, I know. So thank you so much. No. I mean, it doesn't matter. I mean, it's really nice to see you. I mean, Yes, I mean, I think probably, I have not been in touch with you since I've been in Japan, but
of course, you are always there in our
yes.
conversation and in your mind.
Well, yeah, I mean, especially when I talk to Tapan, I mean, and as a matter of fact, I'm doing something with Tapan now. I mean, because a student here, I mean, is working with me on cold atoms and optical lattices.
Mm-hmm.
And he will soon move to, that student will, soon do quantum computing like most of the other students, Yeah, so,
okay.
Yeah. So,
Mm-hmm.
yeah. So how are things going in Goa? Okay.
It's going fine. I've just taken up some additional administration responsibilities. So
I see. Yes.
so it's
Yes,
teaching as in now last 1 year I've not been teaching
Yes.
because of that. But otherwise all fine.
Yes. So very nice to see you, Dilip. I mean, hi. So
I'm in my new place.
yes. So this is your department in Manipur, right?
That's right. So
okay. So
so
you've been there for about a month now, or month and a half?
That's right. About a month now.
Okay.
So right now we are conducting online exams for the first semester.
I see.
Practicals will start soon. Then add some backlog of second semester exams. So
okay. And things are going well, reasonably. In the new department,
going quite okay.
Okay.
And maybe sometime next week we'll start the pre-PhD coursework.
Yeah.
It's a different environment.
Yeah. Did you by any chance, I'm sure you probably know her, Ranjita, who was Vasant's student? Okay.
Oh, yes. I have met her quite a few times.
I see.
In fact, I think she is applying to various places. I'm not very sure about if she has got any offers from anywhere. But yes, I do know her. I have met her once. Oh, that time you were also there in Prasant's conference at Kolkata, ISER Kolkata. So that
no, I couldn't make it actually to that conference. Yeah. She'll be joining Manas as a postdoc.
Okay. I see.
Yeah, I think in a month or so. But that will be sort of jointly between the center that I'll be joining in Kolkata and Manas, because Manas will be in both places.
Okay.
So, it was nice to see all of you and having nice time. So it was pre day this one. So I think now Simran, who is a undergraduate student, so she will be moderating the session. And
okay.
Good morning, everyone. Am I audible?
Yes,
you are audible.
So we'll start in just another 2 minutes.
Okay.
Yes, yeah.
Dilip, you are in office or home?
he is in his office.
He's in office?
Yes. You can.
IRP.
Hi. So this is your office? Yeah, looks like office. Yeah. Good.
So this is my new office room.
I can see that it's well-maintained office.
Well, yeah, can say.
Nice.
How are you?
Fine.
Okay, good. Back home?
Yeah, I will be going office now after listening your time.
Yes. Okay, good.
Simran, you can start.
Okay,
Yeah, we can start. Yeah.
So a very refreshing good morning to one and all present here. On behalf of the organizing committee, I extend you all a warm welcome to the fourth and concluding day of this international conference on fundamental science and quantum technologies using atomic systems. It has indeed been a substantial journey so far. And today, we're again going to have several talks on distinguished topics ranging from quantum phase transitions to many-body physics, followed by a felicitation ceremony at the end. Now, to chair the first half of today's program, we have with us Professor Ramesh Pai, who is an expert in the fields of theoretical condensed matter physics, phase transitions, many-body physics in ultra-cold atoms, etc., to name a few. Currently, he is serving as a senior faculty at Goa University, along with being deputed as a finance officer. Thank you, Professor Pai, for accepting our invitation for being the session chair. Before handing it over to Professor Pai, I would like to remind that the audience can post their queries either in YouTube's comment section or in Zoom's chat window. These questions will then be taken up by Professor Pai with the speaker at the end of the talk. With this, without any further ado, I request Professor Pai to take over the command.
Hello.
Yeah, we are audible.
Okay, we will start or we'll wait for a few more minutes.
Yeah, you can start. I think there are people will be joining later. You can start.
Okay. So good morning, everybody. Let me introduce myself. This is Ramesh Pai from Goa University. I am going to be chairing this section. We have lined up 6 invited talks today, and we will start our first talk by Professor Dilip Angam. He was at PRL Ahmedabad. I've just learned from him that he has shifted to Manipur University recently, just about a month back. So let me welcome Professor Dilip, and he will be talking on a topic which is called the quantum phase transitions at nano Kelvin. Can I hand over the mic to Dilip?
Yeah.
Are you there?
Yes. So let me.
Yes. Okay, I can hear you well. So I will give you some kind of a time warning at around 5 minutes before. So you have got an half an hour. So around 25 minutes pass, I'll just kind of give you some kind of a message. So as far as the questions are concerned, one can type it over the message line. That is probably the best option, and then one can take it up after the talk. Yes, we can see your presentation. Now I'm muting myself so that we can save the bandwidth, and I'm handing over the mic to you, Professor Dilip.
Okay. So thank you, Ramesh, for the kind introduction, and thanks to the organizers for inviting me to give this talk. And I also take this opportunity to wish Bhanu a very bright future after returning to India, as well as the time before returning to India. So it's a good occasion. And so without much ado, let me start my presentation. So what I'll be talking about is quantum phase transitions at nano Kelvin. So here what I'll be doing is that I'll be describing some of the results that we have obtained in the past few years, as well as a part of the ongoing work. So the plan of the talk is that I will give a brief introduction, then I'll come to quantum phase transitions, then I'll just give a brief introduction to optical lattices, and then come to the quantum phases that we have studied in the recent past. So the phase transitions are ubiquitous in nature, and one of the most familiar phase transitions that we encounter is associated with the phases of the water. So the kind of a conventional phase diagram that we come across in textbooks and in various contexts is about this kind of a phase diagram where you have solid, liquid, and water. And this point, that is the critical point, is of great interest, as well as this critical triple point. But if you look further and then consider the general or the most general phase diagram of water, then it's not this simple, but rather it will be like this, where in the crystalline phase of the water, there are several phases that can occur at different pressures. So this is to emphasize that other than the phase transitions that we are familiar with, different materials exhibit phase transitions at different pressures and temperatures, which may be of importance to understand the properties of the matter in much better detail. So the phase transitions are essentially driven by thermal fluctuations that we are familiar with, that is to do with the occurrence of different phases with a change in the temperature. So we identify various phase transitions depending on the discontinuity of the free energy derivatives. What is of importance to us is the second class of phase transitions, which were originally classified under second and higher order phase transitions, which in the present context of critical phenomena and phase transitions are generally clubbed as continuous phase transitions. So what is so important in the phases or in identifying the phases is that associated with each phase, there is an order parameter that can be identified uniquely. So in the case of the thermodynamic phase transitions, the phase transitions which are driven by the thermal fluctuations, as we change the temperature, what we see here is that the jiggling motion of the atoms and molecules in the system, they undergo a change, and associated with change, there will be these phase transitions. But the other possible phase transition that can occur is driven by the quantum fluctuations. And another example of a thermal phase transition is associated with the Ising model, a very well-known phase transition, where there is a transition from a paramagnetic phase to a ferromagnetic phase when the temperature is decreased below a critical temperature. Now, what we are now interested in is in terms of the quantum phase transitions. The quantum phase transitions of late has played a very important role in the context of these ultra-cold atomic systems. Now, the kind of temperatures that we are interested in is of the order of 100 nanokelvin or below, a temperature at which a dilute gas of atoms will undergo Bose-Einstein condensate. Now, this kind of a Bose-Einstein condensate of dilute atomic gases is very different from the condensation that we normally see in liquid helium-4. In the case of the liquid helium-4, there is a strong interaction between the helium atoms. So there is a background strong interaction. And because of the quantum depletion, the fraction of the Bose-Einstein condensate is below 20%. But the nice thing about these dilute quantum atomic gases is that the BEC in these, or the fraction of the BEC in these, could be as high as 100% or very close to 100%. So the kind of system that we're interested in is these ultra-cold atoms, which are filled in optical lattices. And these systems are quite appropriate, quite apt to explore quantum phase transitions. Now, in the case of the quantum phase transitions, these are a class of phase transitions that occur at zero temperature, where the quantum fluctuations drives the transition from one phase to another phase by a change in the parameter of the system. So this is what we are interested in. That is a class of phase transitions driven by quantum fluctuations. Now, why is it important to study quantum phase transitions? The quantum phase transitions are essential for a deeper understanding of the various quantum phases of these systems, that is in the context of ultra-cold atoms, are important in order to use these systems in quantum devices. That is to say that if we have a quantum device that is made out of these ultra-cold systems, as we tune the parameters, is it possible that the system will undergo quantum phase transitions, which is detrimental to the kind of achievement that or design of devices that we wish to make? Or are there some phases which are stable against the environmental factors? So with this in mind, it is essential that we have a deeper understanding of the quantum phases of these systems, which are turning out to be promising candidates to design quantum devices. As well as in other areas of condensed matter physics, understanding of quantum phase transitions is also important to sort of look at other unsolved properties like high temperature superconductivity. So there are these connections and the requirements in terms of applications of devices as well as fundamental unsolved problems. Now, what is also important is that we have all of these possible thermal phase transitions and quantum phase transitions, but is there something that is a commonality that defines all of these phase transitions? So that part comes under the domain of critical phenomena. So at the phase transitions, what we have is that there are these various thermodynamic quantities and correlation properties that shows a divergence if it is a continuous phase transition. That is to say that in the context of the Ehrenfest criterion for the phase transition, that is second and higher order phase transitions, do show these kind of divergences of the thermodynamic properties and correlation and dynamical properties. So these are essentially identified by some critical exponents. So that is what we will be interested in. That is the critical exponents associated with quantum phase transition and various possible realizations of quantum phases in these optical lattice systems. That is what we are interested in. Now, what are critical exponents? As I was saying, they have these thermodynamical properties, correlation properties, and the dynamical correlation properties. They diverge. And if A of t is one of those quantities, and t is what is referred to a reduced distance or reduced parameter, in the case of the thermal phase transition, it is defined with respect to the critical temperature, and it essentially shows, or it is a measure of the distance from the point of the transition. So the beauty of this kind of divergence is that the critical exponent alpha, which determines the divergence of the thermodynamical property, is independent of the microscopic details, but it is dependent on the symmetry of the properties, or rather some of the macroscopic properties. So what can happen is that there can be different systems that shows different phase transitions, but if they do have the same symmetries and the macroscopic properties, then they belong to the same universality class. So an example would be, an example of a universality class would be the Ising model, that is a system of classical spins. They have the same critical exponents as a beta brass. Beta brass is essentially a mixture of two metals that forms an alloy, and depending on the temperature, this alloy has two phases. One phase is where the component metals, that is this copper and aluminum, they separate out, and in another case, they mix. So this, which is a really different kind of a material, does have the same critical exponents as that of an Ising model, which is a system of spin. So these two different, highly different systems are governed in terms of the divergence of their thermodynamic properties by the same critical exponents. So this is the universality class. So the same universality class can be extended to the case of quantum phase transitions as well. Now, in the context of the ultra-cold atoms, what we can think about is a collection of these ultra-cold atoms trapped in an undulating potential created by counter-propagating laser beams, which is referred to as optical lattice. And this kind of a system shows two quantum phases, that is small insulator and a superfluid. That is one of the simplest models in the case of the optical lattices. And this has the same universality class as the XY model. Now, the beauty of this kind of a universality class is that by looking at the properties of a simplified model that belongs to the same universality class, we can get a good insight on much more complicated system. So the universality class plays an important role in terms of understanding the phase transitions, whether it is thermal phase transition or the quantum phase transitions. Now, this is how it looks like. Supposing if you look at the quantum phase transition, then the phase diagram would simply look like this, because what is generally defined is that the quantum phase transitions occur at 0 temperature. So if we have a system and we have one of the parameters G, which can be controlled, then in this phase diagram, what it indicates is that there is a quantum phase transition as the parameter G crosses GC. But then it will not be so simple if we introduce thermal fluctuations in the system. The finite temperature also plays an important role, and there will be a competition between the quantum fluctuations and the thermal fluctuations, and there will be some domain where the signatures of the quantum phase transitions will be prevalent in the thermal domain as well, or in the finite temperature domain as well. So that is what is of interest. Now, optical lattices, as I was mentioning earlier, are system of undulating intensity field created by counter-propagating laser beams. And in these intensity variations, atoms can be trapped, and some of these realizations and experiments could be as complicated as these. But the kind of physics that can be explored in such a system is many, and it also holds the promise of realizing many of the future advanced quantum devices, as well as simulating strongly correlated systems which are of interest in condensed matter systems. Now, one can ask the question, why optical lattices? The beauty of these optical lattices is that the system has many controllable parameters. It could be in terms of the interparticle interaction. It could be the number of particles, the lattice geometry. That is, we can have a lattice that starts with a square in geometry, but that can be transformed to a hexagonal or to a triangular lattice. Now, such kind of versatility is not to be found in true condensed matter systems, but we have this kind of a flexibility in these optical lattices. Not only that, we can also change the lattice depth through which we can control the hopping parameter. Then we can also introduce synthetic magnetic field. And in the case of the synthetic magnetic field, the important point is that we can introduce an equivalence of magnetic field that is not possible in conventional condensed matter systems. So this kind of a realization promises the possibility of exploring, say, topological phases like fractional quantum Hall effects of very high field per placket. The other thing is that the optical lattices are almost devoid of defects, and there is a possibility of having a large number of internal states. So now let me come to the examples of which we have studied. So one of the starting point is this Bose-Hubbard model. In the case of Bose-Hubbard model, what we have looked at is essentially a square lattice where we have the first term, that is the hopping term, that is atoms are allowed to hop from one lattice site to the nearest lattice site. And then we have this term, which is essentially on-site interaction. So the Hamiltonian of a Hubbard model, or the system where we have an optical lattice filled with atoms at very low temperatures, is very well modeled by this kind of a Hamiltonian, where we have a hopping term that is essentially the kinetic energy term, and then we have the on-site interaction term, which is schematically represented in this hopping term and an interaction term. So this kind of a system exhibits two quantum phases which have been experimentally verified. That is the Mott insulating phase, where in the case of the Mott insulating phase, there is a commensurate occupation of all the lattice sites by atoms. That is to say that if we have a Mott insulating phase of 1, then all the lattice sites are occupied by a single atom at its lattice site. So in this case, what happens is that there is a coherence in the number, but since the phase is the conjugate variable of the system, the phase is not coherent. But on the other hand, we have another phase that is possible from this system where the number of particles at its lattice sites is not fixed, and hence number is not coherent. But on the other hand, the phase is coherent. So these are two possible phases that are observed in the Bose-Hubbard model, the simplest model. But now from here, what we can do is that we can introduce disorder to the system. Now, this is somewhat connected to the condensed matter realizations, where in the case of the condensed matter realizations, it will never be as clean as what we had looked at before, that is the Bose-Hubbard model. So in this case, in experimental systems, the disorder can be introduced in two ways. One is truly random, that can be created by some sort of a random optical field. The other is a pseudo-random, just like as in the case of an Aubrey-Andre model. But here what we are looking at is a truly random, and that too what is referred to as a quenched disorder. In the case of a quenched disorder, what we have is that we have disorder in the system that is independent of time. Now, this kind of a quenched disorder system does have some challenges in terms of calculating properties, because we cannot do a thermal averaging. So what we need to do is we need to do an ensemble averaging. That is, we need to take as many realizations as possible, and then we have to do an ensemble average. So in this system, what is important is that a new quantum phase emerges in the system, and that is referred to as a Bose glass. In the case of a Bose glass phase, which occurs in between these two Mott lobes, what we have is we have puddles of superfluid phases, and as we increase the random potential, what we find is that the Bose glass phase, the domain of the Bose glass phase increases. So D is essentially a measure of the disorder that is introduced to the system, and as we keep on increasing here, for example, so we see a large portion which exhibits Bose glass phase. Now, the importance of the Bose glass phase is that this phase is rather stable. So what it means is that supposing if we have a quantum system, and if we wish to have some sort of a memory device, then we need states of the system which are relatively stable against external forces or external perturbations. Now, this kind of a phase, that is the Bose glass phase, is such that it will be relatively stable against external perturbations. So in this context, in order to devise stable, or in order to devise memory, which implies that it should be, or the system should be stable against external perturbations, these kind of phases are important. Now, what we can do next is that we can fine-tune this interaction between the particles. Rather than it being on site, what we can now introduce is a long-range interaction. The long-range interaction that we can consider is to have a dipolar bosons, and a very simplified model of that is to consider the next nearest neighbor, or the extended Bose-Hubbard model. Now, this kind of an extended Bose-Hubbard model, where we have just introduced the nearest neighbor interaction, provides a very qualitative understanding of dipolar bosons. The reason is that in the case of a dipolar interaction, it decays as 1 by r cube. So the interactions from the next to nearest neighbor, though it is important, may not be so large. So as a starting point, if you truncate this dipolar interaction to the nearest neighbor, it does provide a very good qualitative understanding of the different quantum phases that emerges in this system. Now, compared to the Bose-Hubbard model, where the interaction was essentially on-site, if you introduce this nearest neighbor interaction, or in the extended Bose-Hubbard model, there are two new quantum phases that emerges in the system. One is a supersolid, and one is the density wave. Now, density wave is a solid phase, or it is an incompressible phase, or in other words, it's an insulating phase that has a gap. But in the case of the supersolid, what we have is there is a simultaneous existence of diagonal order, that is to say that there is a periodic pattern of the density, as well as there is an off-diagonal long-range order. The off-diagonal long-range order is associated with the
Angam, I think you have 5 more minutes.
Okay, so this is one thing. So this is the phase diagram that we have in the context of this extended Bose-Hubbard model. Then what we can do is that we can genuinely consider the dipolar bosons. And then in the case of the dipolar bosons, what we also have is another parameter, that is the tilt angle of these dipoles. So with that, what we'll have is we'll have this kind of a schematic representation. You have the dipoles, now they can tilt, and their tilt angle can be controlled by applying an external magnetic field. And this leads to the introduction of different phases, which are essentially supersolid, but of different density order. And we can also have what is referred to as emulsion phase. So this is what is important in this. And the phase diagram looks a little complicated like this. It harbors many quantum phases. So this is with dipolar bosons, where we have the tilt angle controlled. Then we can also have two species in the system. Now, about the two species, what we'll now have is that we have to extend the Bose-Hubbard model to two species and their interspecies interaction. Now, in such a system, the important or the interesting part is that, is it possible to have a phase where there is a spatial phase separation of the densities? And that's what we have shown. So we see that there is a spatial separation of the phases, and this essentially is controlled by the on-site interaction. That is to say that we expect that these phases will appear because of the long-range interaction. But what we have noticed is that the on-site interaction itself can drive this kind of a phase separation, where there is a spatial phase separation. That is, one part of the lattice is occupied by one of the species, then the other part is occupied by the other species. Now, the last thing that I'll mention about is that once we introduce the magnetic field, that is like a static background field, then there are topological phases that emerge in the system, and those are of various types of quantum Hall phases, integer and a fractional quantum Hall effect. So the way how to identify this is based on the correlations. In the case of a quantum Hall state, the correlation does not show a monotonic decrease. So this is how it will look like. That will not be the case. Now, obtaining a good or obtaining reliable fractional quantum Hall states or integer quantum Hall states is a little tricky, in the sense that it is highly correlated system. So all the possible bases of the system, they contribute. So for this, what we have done is that we have used an exact diagonalization, and we have looked at the various properties, including Chern number and so on. And we do find that there are certain fractional quantum Hall states, in particular where alpha, that is the magnetic flux, that is equal to 1/4. And with these filling factors, that is nu, these are realizable. So these are the various possible quantum phases that we have observed in different settings with the starting point of Bose-Hubbard model and then applying various complications to the systems, whether it be in terms of the form of the interaction, the form of the trapping potential with randomness, or in terms of the range of the interaction, or in terms of introducing a background static magnetic field, that is a synthetic magnetic.
Angam, I think your time is up.
Okay, so I'm done.
Right. So thank you very much for this wonderful introduction to the quantum phase transitions and some of the work which you have done. It's very exciting. We have a couple of questions, but first let me ask you one quick questions. That is from a Koel D on a YouTube channel when he was watching. This is how 0K is not possible to achieve experimentally, how quantum phase transition can be used in devices. So if you have a quick answer to that, then we can move on to the next.
Yeah, so that's a very good question. Yes, what we normally look at when we normally look at quantum phase transitions, we do study it at 0 temperature. But as you're saying, it should be at finite temperature. So what is important is that, as I was showing earlier, so there was this schematic representation, this one. So this is what we will see in the case of an ideal quantum phase transitions. But we will also have thermal fluctuations. So there will be some domain where the signatures of the quantum phase transition will be observable, and that is where we are interested. So that is to say that when the temperatures are very low, when the quantum fluctuations are very important, this implies that in the case of the optical systems, at around 12 nanokelvin or so, the quantum fluctuations are going to be quite significant. So in that domain, these quantum phase transitions will be important. And in fact, this MI to SF, which is essentially a quantum phase transition, has been observed in experiments.
Thank you. We have actually a couple of more questions, but because of the lack of time, I think I should move ahead. And we probably, if we can take that at the break time. Unfortunately, coffee break questions are more common, but let us see whether we can take up those questions during the tea break.
Okay.
So thank you again, Dilip, for this wonderful talk.
Yeah.
So let's move ahead for our second talk. We have Dr. Manas Mukherjee from the Center for Quantum Technologies, National University of Singapore. He is going to talk on the ion trap quantum sensing and simulation, a discussion on ion qubit and its application. Dr. Manas Mukherjee, can you hear me?
Yes, I do. Thank you.
Thank you. So I'm muting now myself and handing over the mic to you.
Yeah, thanks. That would be a real hardware thing, but now we do it software. Okay, thank you very much.
Right. Okay, thank you. Thank you. So you have 25 minutes and the 5 minutes for questions. So I will give you some kind of a warning at the 20 minutes time.
Perfect.
All right.
Okay, good.
I'm handing over to you.
Yeah. So let's start. First of all, I would like to thank the organizer for this wonderful web series, as we can see it. The topic of my discussion today would be around sensing and simulation, but this may be a little ambitious, as you will see it later. First of all, again, thanks for the invitation, and also happy birthday to BPD. But we will see what we can do afterwards. Okay, now this is sort of the team before COVID, and it also has changed over time. But what I will talk mainly about is work from Taeyoon Yum, who is now in Korea, Jesper Pua doing his PhD, Torun, who is a postdoc now, and Noah, his PhD work. Okay, so what I'm going to talk about is related to three things, but all having the common base, which is trapped ion. One can think of these are like atoms, just charged atoms. which can be manipulated in a very pristine condition. So in terms of quantum sensing in particular, I will get back in a minute. But then the other two topics, which is one on quantum simulation, is based on demonstrating a heat engine, which is working in the quantum regime. And the last part is how we would do is in the next steps, and sort of giving a glimpse of what we are working on at present and what we will be doing in next few months. Yeah. However, as I understand, there is 25 minutes. This is too ambitious. So what I will actually do, unfortunately, is only talk about the sensing part. Yeah. Now, just to start it, I would say that we are in a very exciting time in terms of quantum technologies in general. And that has quite a number of reasons. The one reason which is something of my favorite is because we are going through the second revolution in quantum technologies, and Alan Aspey had coined the aspect that if you think of the first revolution, when we used the wave particle duality mostly for technological purposes like lasers or even transistors, this time it is slightly different, and actually philosophically it's completely different. It uses certain resources like superposition and entanglement. However, the biggest challenge that we have at present is to define a problem where quantum gives us advantage compared to the classical systems. And it's not a very easy solution to it. When we see this from the quantum computing side, when you have a large enough quantum computers with good enough quantum volume, one could surpass the classical problems, but one has to also define what classical problem is of real importance, which a classical computer cannot solve, which might take some time to get to that supremacy. However, there is similar challenge also in the other quantum technologies, and one particular one is sensing, where one has to find problem where classical sensors can be surpassed. Now, the classical sensors have developed over years, and they are very, very good. So one has to be better than those. And here is one such example where you can actually go beyond any classical sensing and show that the quantum has real advantage. Now, for those who are rather junior in the audience, this is a bit of initial ideas about how our AND trap work. So the whole, what you see here is the potential which you generate by applying radio frequency voltages to the traps. I will come to that physical realization later. That creates a time-dependent simple harmonic oscillator potential, which you see as the black curve. And you see the ball is making a sinusoidal oscillation, but at the edges, it makes a little bit of jitter, and those are driven motion called this micro motion, while you see the large oscillation, that's the macro motion or secular motion. That forms one part, which is the external motion of the trap. The second quantum state which we work on are the internal state of the atom. In this case, it's a 138 barium plus. And we laser cool it by using S to P transition and P to D transition as a repumper. Now, if you look at from the viewpoint of a theorist, if you cool the ion, they go from a state, a motional state, which is given by the red graph here, which is probability to be in these ladder structures, N level of the harmonic oscillator. And we cool it down to the first one you see is after Doppler cooling. The second blue color one is more after ground state cooling. So we can actually cool it down to the ground state of this harmonic oscillator. So you have now a quantized oscillation. So you can go one by one steps on these phonons or vibrational modes. You can also use the internal state, which we use as a qubit. Yeah? And in particular, you use the S half minus half to D 5 half minus 5 half. So this is a magnetically sensitive transition, but it's a very good qubit because just looking at this qubit leaves for 30 seconds, which is the T1 time, if you want to compare it to any qubit. Yeah. So as you can see, you have a system which provides you two in one. One is the external motion, which is quantized, the internal motion, which is also quantized. So you have a qubit and you have a harmonic oscillator. For our talk here, most of the parts, since we will be talking about the sensing, we would not bother much about the external motion. But if you would like to know more about the heat engine simulation, that's on the external motion, where the phonons are used. In this particular talk, we would be mostly using the qubit itself. Okay, so this is the real stuff, how the trap looks like. It's a very ordinary blade trap where the radio frequency voltage is applied on these blades, and there are two end caps to produce the longitudinal potential. And you can trap them and produce linear crystals of large sizes. So what is of importance now is a very simple two-level system, as you can see here. And what we are interested in is to measure a time-dependent field, which is given by this wave on the background. And it is small compared to the energy splitting here. Because of this field, the levels, they oscillate because this is time dependent and it couples to the state and it oscillates. Another way to look at it is a simple example of a B field and a spin which precesses. Now imagine that the B field is not constant in time, but has a sine component with omega frequency and B1 as the amplitude. Right, so what would happen is the spin would precess, but it would also oscillate at a frequency given by the omega. Now, the interest here is to know what would be the minimum uncertainty with which we can measure the omega and the B1. So that's what falls under the domain of parameter estimation, if you think of it from the quantum information point of view. So from there, we can actually, there is a very well-developed theory of parameter estimation. And any parameter, for example, the B1 or the omega, is now represented by an alpha. So the variance of that is bounded by 1 over n F alpha, where F alpha is the Fisher information, which is bounded by Kramer's Rao bound, while the n is the number of measurements one takes. And the quantum Fisher information is given by this expression, where psi is the state of the probe, the quantum state of the probe. Okay. So for time-independent Hamiltonian, meaning that the Hamiltonian do not contain any cosine omega t terms explicitly or any t dependence explicitly, the F alpha would be proportional to t square. And that leads us to this limit, which we know as the standard deviation for the alpha would be bounded by 1 over square root of n, that's the short noise limit, and the 1 over t, the time for a single measurement. Now, this F alpha, or the quantum Fisher information, can be rewritten in a different way. So depending on the technique you use, you can actually express it in different forms. In particular, the best known technique is the Ramsey technique, by which you can measure this alpha. It could be the frequency, it could be amplitude. And what is the Ramsey technique? The Ramsey technique is basically you start with a superposition state and freely evolve under a Hamiltonian, which is time dependent or independent. And then you measure this awkward phase during the free evolution. And the quantum Fisher information is a product of the P0, P1 and the sensitivity of your probe or the technique. To that parameter. Now, this is maximized when P0 and P1 are 1/2. Now, another thing to note is that the delta alpha, which is the uncertainty, is related to the inverse of the sensitivity. So we'll come to this later. Now, usually the experiment would go this way, that you start in the equator let it freely evolve, and then you finally measure the acquired phase. Now, since the Hamiltonian, in case if it is independent of time, you can see the phase is proportional to t, and that's how we get. And you get 1 over t coherence time. The situation is different if it is a time-dependent Hamiltonian, because now during the free evolution, the spin is also jittering about a central point, which means whatever phase it acquires in one half of the cycle is removed in the other half. Another way to look at it is the eigenstates of the derivative with respect to the omega, and that is a sinusoidal in nature. So you can see that any eigenstate would be evolving, but each cycle, half of the cycle, it acquires phase, in the other half it removes the phase. So if you look at the total phase acquired, which is another way the quantum Fisher information itself, it scales as t square, but provided your measurement is done at the right phase. So how do you overcome this? There was an experiment by Smith et al., which was with a single nanoscale quantum sensor. But in this case, the Hamiltonian itself was explicitly non-linearly dependent on t. Now, if such an Hamiltonian is used, you can show that it's trivially, you can go faster than t square. For a linear one, not a linear, but if the is not non-linear, but if your B1 is small, in that case, one could use what was proposed by Pang et al., that what is called feedback, quantum feedback, to acquire more phase within half of the period. And we implemented this scheme for the AC stock shift measurement, which has noise, as we'll see it, at 50 kilohertz. Sorry. So the experiment goes in the same way. However, you apply pi pulses every node or antinode of the eigenstates. So which means whenever a phase is acquired, before it crosses over to the negative phase, you flip the spin so that you keep on acquiring the phase all the time. But of course, you can also see that if you do that, you increase the acquired phase, or the QFI increases at a much faster scale, which is scales as T4. But there is a cost to it, and the cost is this is an adaptive measurement. You roughly have to know what is the frequency of the noise that you are looking at. So from the experimental point of view, one thing you have to ensure is that your experiment do not have any other systematics, which is ensured by the short noise limited delta phi measurement, or the phase measurement. And this is the number of measurements you take, and this is the uncertainty on the phase, and it scales as 1 over square root of n, which tells you that your measurement of the phase is short noise limited. Then if you change or vary the external adaptive measurement frequency, then you get the phase acquired during that linear variation of f. The slope of it provides you the sensitivity. Now, if you plot the sensitivity, or inverse of it would be the precision, you can see that as time increases, so the longer you observe it, the sensitivity scales as 1 over t in case of if you do not apply any feedback to the system. But if you apply the feedback, you can actually scale it as 1 over t square, which means that if you have a B field sensitivity of some femtotesla, this for the same time you would have at least a factor of 4 or 5 more, and if you go higher, this can be order of magnitude faster. Now, this is more or less the limit that you can get from any Ramsey type of experiment, and that is more or less the limit that you can have in any experiment. Now, you can beat that limit provided you have feedback. One thing to note that this is not applicable for any clocks, because the clocks are time independent fields, Hamiltonian. This is only applicable if it is a noise to the clock. Similarly, for the P1, it doesn't scale at all, and it can be shown that the quantum Fisher information is independent of the time in case of the magnitude, while it scales as 1/t if you apply a feedback. Now, this is very similar if you would have done a lock-in amplifier. A lock-in amplifier is basically, in classically, it means that if you have a signal which is below the noise, but you know roughly the frequency at which the noise is or the signal is, you can actually mix it with that frequency and get out or amplify only the signal without the noise. This is very similar, but in the quantum domain. So from there, we could actually show that our scaling is 1.75 in this particular experiment. You could actually improve to 2, which is the maximum bound of it. And the main reason why we are limited to this is that roughly in here, the decoherence sets in as we are working with a high qubit. So we are working in this particular case with a fast qubit, which decoheres faster. Okay, so the application of this are numerous. So just to give you an idea, it could be used because now you can sense a very small electromagnetic field which could couple to the spin of the atom. Then you can actually look into certain types of dark matter fields, and I will explain a little bit more on that. The other applications are low frequency magnetic field noise. Now, I would not get into details, but there are defense applications from those sides. The other more normal applications would be the noise analysis of a qubit. For example, if your qubit is having a noise which is close to one of the sidebands, you could actually analyze what frequency it has and then try to mitigate it. So this curve shows here that by scanning the phase as well as the frequency, you can actually precisely know the exact phase and the frequency of the unknown noise. In this particular case, it was 50 kilohertz. Now, a little bit about the dark matter field. So we were in particular looking into the weakly interacting sub-eV or WISP particles. Now, these would have an effect on any probe, any spin probe. It is quite matured in terms of experiments with nucleons or nuclear spins, and it is considered to be a classical sine field which interacts with the nuclear spin. In the same token, one could think of the spin interacting with the electron spin interacting with the background GAE. These two are different because the coupling constants are different. And if you look at the coupling constant, it's roughly supposed to be around whatever you can plug in this number to be unity. It's a very small 10⁻⁹. Now, the mass range is a very interesting one. It's from kilohertz to gigahertz where they expect it to be. Now, this is also interesting because if you look back into the oscillation, so if you think of this as a noise, the mass is, or the frequency of the noise is exactly the mass of the predicted dark matter. So in our experiment, of course, we are nowhere close to where you could, where the predictions are. However, one should also see that this is the only direct experiment till now. Whatever is known for the electron coupling is only from astrophysical sources. The ALP dark matter would be interesting over here, and that's a limit. It's one of the strong limits are given by the white dwarf, but then again, it's based on astrophysical models. Yeah. So we stand over here. As you can see, it's far away from we need to be here. However, this is still a long way to go, but in principle, the same principle could work on a large atomic magnetometer, but the protocol remaining the same, which could pull up to here or even here. Okay, with that, I would conclude because I think I'm just on time. So, so what does it tell us is that if you take a qubit, a simple qubit as a probe, but if you apply quantum feedback, it is indeed possible to surpass the usual limit of the sensitivity that you can get in a normal classical or even quantum probes and go beyond it. Yeah. It is limited even by the coherence time for a single measurement. However, if you have larger number of spins which are coherently oscillating, you can apply the same protocol and actually go far beyond the present capabilities in order to reach to the boundary where things could be very interesting and competing for a direct measurement of the ALP dark matter field interacting with electron spin. With that, I would like to thank our collaborators and in different and also the funding agencies for supporting our work. Thank you.
Thank you, Manas, for this wonderful talk. I haven't got any questions on my message.
There is one in.
So let me open it for the audience. If any one of you want.
No, there is
to
one
ask,
in YouTube.
There's one in YouTube. Okay.
One in
there
YouTube.
Too many things.
Okay. Yeah, I just got it. Let me just read it. If we apply the pi pulse, will only the electron spin change in the block sphere or something else?
Right. So what is happening is, I guess people are more familiar with the spin echo. So in spin echo, what you do is in the block sphere, it rotates. I don't know if you can see me, or
Yes,
it rotates in the equator, right? But now if you have a time-dependent field, it would be jittering while it is rotating. Now, what you are doing is your pi pulses, unlike in case of spin echo, where you remove the noise frequency by doing a pi pulse, you acquire it before it crosses over to the other phase. So each time you do a pi, you actually rotate it to the other extreme and increase the phase that you are acquiring, but at a given phase.
Okay, there is another question from Ravindra Pratap Singh. Can you give the order of the frequency when you say extreme to W frequency, omega frequency?
Right. Thanks, RP. So yeah, the frequency range is that you can use is really dependent on the coherence time, because as you can see, you lose this the sensitivity as decoherence sets in. Usually our decoherence time for the ions can be as long as milliseconds, but in this particular case we were looking at 50 kilohertz, which for which we wanted to drive the qubit faster, and that's limited to 80 microseconds around, 80 or 100 microseconds around. Now, if you think of milliseconds, that's sort of the limit till which you can look into the frequencies. So if you have one pi pulse in the whole cycle, then it's half of the, so 500 microsecond would be the 1 over 500 microsecond would be the frequency. But in fact, it is all can be increased.
Okay, thank you, Manas.
Yeah, there is also a question from Shankar. Manas, you are there still, or you have lost?
Yeah, I'm here.
Yeah. You mentioned about the atomic magnetometry to enhance the limit, if I understand correctly. Can you please elaborate a bit on this issue?
Thanks, Shankar. If you look at how we can go to the next steps, it's the T is limited by T coherence. Yeah? The next phase of improving it would be the N. Yeah? So if you could increase the N number while still keeping your T coherence long, but applying the same trick of the feedback or lock-in amplifier, you can actually increase by this number N, square root of N. So for the atomic cell magnetometry, if you have 10 power 20 atoms, you can increase by that large number. Yeah.
Yeah. So this question is from Saikant Ghosh. Can you have sub short noise scaling with the classical feedbacks? How small of a magnetic field can you measure currently and at what frequency?
Right. So first, the short noise limit. So you can see the thanks, Shaikat. So you can see here the we are short noise limited for the phase measurement, and that's not going to be changed. So what is improving is for the time dependent field. The gain is on the time scaling. So it's basically the Heisenberg scaling. Now coming to the actual magnetic field, we did not do this experiment on magnetic field, but our next experiment is from the defense side. It's more on the magnetic field. So for our experiment, it was AC stock shift, so EM field noise. And in that case, it is, as you can see, it's what if, so the sensitivity is of phi. Now you can think of, instead of F, you can have a B field, or more on this side, right? So the omega D could be changed by a B field, but then the sensitivity, whatever you have in your probe, is not going to change. What you are gaining is, in a shorter time, you have the same sensitivity, which means if you think of it as a measurement till your coherence time, the increase in sensitivity is what is given over here. The difference between the red and the blue. Now, of course, it changes depending on the B fields or how you probe it. Yeah? So I would imagine for unusual atomic magnetometers, if they go to femtotesla, you can go to femtotesla in a shorter time. For the same time of coherence, it would be orders of magnitude higher or lower.
Thank you, Manas. I think because of the shortage of time, I think we can't take any more questions at the moment. Thank you, everybody, those who have asked questions, and this was a wonderful talk. Thank you, Manas. So let's carry on with our third talk before the break today. This is Dr. Minori Abe. I hope I have pronounced it correctly. His affiliation, Department of Chemistry, Tokyo Metropolitan University, Japan. And the title of the talk is going to be Reconsideration of the Electronic Term of the Shift Moment in Closed Shell Molecules. Dr. Abe, am I audible to you?
Yes. Thank you.
Okay. Yes. I'm here.
Okay, let me share my screen.
So welcome to this program. So I will mute now. You have basically 30 minutes, which is basically 25 minutes talk and a 5 minutes question section. So I kind of come back at the end of 20 minutes. So that will be kind of a signal to you that you have another 5 minutes.
Thank you.
Thank you. I'm handing over to you now,
right.
Dr. Abe. Yes, we can see your slides.
Okay.
Yes. Yeah, please.
Okay.
Carry on.
Okay, thank you very much, Chairperson Professor Pai. Hello everybody. I'm Minori Abe from Tokyo Metropolitan University, And I'm really happy to join this great conference. And I'd like to thank all the organizers having a lot of efforts for this conference. And I just want to introduce this photo. It's taken in an Indian restaurant, Maharaja, but located in Tokyo. And we took it in the last year when my friend, Dr. Gita Kopakuma, came back to Tokyo. Also, I'd like to celebrate Professor Dust. Happy birthday. So today I want to talk about the nuclear EDM in closed shell molecular systems. So first I will give a general background of EDM. And second, I will talk about our results, accurate determination of parameter X, which is calculated from electronic wave functions. And finally, I will talk about reconsideration of representation of X formula for shift moment property. And this work is collaborated with my students, Mr. Tsutsui, Mr. Fujita, Mr. Tomiyama, and also Professor Hada in Tokyo Metropolitan University. And also I'd like to thank to Professor Das, Dr. Ikman, Dr. Kendayor, Professor Yoshinaga, Dr. Yanase, and Dr. Marguta for their very important discussions. Thank you. So I wanted to talk about electric dipole moment called EDM of fundamental particles. And if we assume that a fundamental particle has an EDM, then it is parallel to spin axis. Then if we consider the time reversal operation, then the direction of spin turns to opposite, but the EDM remains same. So if we measure the EDM along with spin axis, then EDM becomes minus D. So therefore, if we can measure non-zero value of EDM, it means time symmetry violation, and which is maybe equivalent to CP symmetry violation under the hypothesis of CPT theorem. And currently, there are many experiments, but we have not yet observed any absolute determined values for EDM, but upper limit can be estimated from the experimental errors. And in the case of open shell systems, here, we can measure electron EDM mainly, and precise measurements are done in thallium atoms or thorium oxide, hafnium plus molecules. And you can see that molecular system has lower electrons EDM than the atomic case. And in the case of closed shell systems, we may measure the nuclear EDM, and we don't have very much accurate experimental observation in molecules, but in the case of atoms, we have very nice results, xenon or mercury here. So at present, there is no good results for closed shell molecule, but I think it would be ongoing, and I can find a paper about thallium fluoride in 2012 by Hunter et al. So I hope closed shell molecular experiments are also ongoing. In the case of nuclear EDM, so not like electron EDM, there are a lot of particles in the nucleus. So, and there are many CP violating source in nuclear EDM. And here I only focused on two sources of nuclear EDM. And the first one is called volume effect, which is due to proton and neutron EDM. So suppose this blue circle is a nucleus, and it contains protons and neutrons, and each protons, neutrons has each EDM. So we can combine all EDM and create one big nucleus EDM. Another EDM is called shift moment effect. This is due to asymmetry of proton charge. For example, in this nucleus, if proton locates from here, then there should be some charge distribution asymmetric charge distribution, then it will create a nuclear EDM like this. Then if thorium nucleus has a nuclear EDM D like this, then if we create thorium fluoride molecule like this, then in this molecule, so this is a fluoride nucleus, this is thorium nucleus, then in these nuclei, we have more electrons, and these electrons create electric field at the position of nucleus. So this nuclear EDM interact with electric dipole moment, electric field by electrons, then there should be an interaction energy. And this energy is observable in experiment. And this is very schematic explanation. And in reality, it's a little bit more complicated. And the experimental observable delta E is described Rx or minus 6qx for volume effect and shift moment effect. And here R and Q are the parameters from nuclear wave functions, psi n. And this X is a parameter calculated from electronic wave functions. And if this X value is large, then experimental measurable value, delta E is also large. So if we can find a molecule with large X value, it would be also good experimental systems. Then how this X is represented, then this is based on Heinz-Sanders paper, 1980. And X is described like this as a derivative of rho zero, its electron density at the center of nucleus with respect to molecular axis. So that is taken as the molecular axis, for example, in the thorium fluoride case, axis from thorium nucleus to fluoride nucleus. Then because X contains electron density at the nucleus, this is affected by relativity very much. So we should be very careful to consider relativistic quantum effects. And the pioneering works are done by Quiney et al. They are working on thorium fluoride molecule based on the Dirac-Fock method, but they don't consider electron correlation. And later, Petrov or Kudashov did two-component CCST method, very high level of electron correlation method for thorium fluoride or radium oxide molecules. But their method is based on GRECP or two-component, then it's not Dirac-Fock. So electron correlation was not taken into account at the Dirac level so far. And here's the Dirac equations. It looks like simple, but if we describe the correctly, it has four-component vector form in the wave function. So in the case of Schrödinger equation, we can obtain one function, but in the case of Dirac, we have to obtain four different functions. So it's a time-consuming process. And also, I introduced coupled cluster singles and doubles method, which wave function is defined as exponential T1 plus T2 hat and Hartree-Fock determinants, where T1 and T2 is described like singly excited determinants or doubly excited determinants. And this is an effective method when the Hartree-Fock determinant is the only dominant determinant. So our objective is develop the program to calculate X values at the four-component Dirac and CCSD level. And we determine the most accurate value of X for thorium F and other molecules. And I'd like to notice that to you that we have to be very careful to pick up the proper basis sets, because this X depends on the electronic wave function at the vicinity of the nucleus. So general Gaussian basis sets, so-called CCP-VQZ or dial-QZ, those are really accurate but in general case, but it's not okay for this X property, because this is obtained from the energy optimized to be lowering energy. And so we have to use even tempered basis set that is already proposed by Quine et al. So in the previous work, so we use their same basis set following. Then here's the results. So just for comparison, I calculate the diol QZ also, and even tempered plus polarization basis sets. And if we compare the basis sets difference, then we can find that quite large difference between diol QZ and even tempered basis sets, both at the Dirac-Fock or couple class levels. And if we compare the electron correlation effect from Dirac-Fock to CCSD, then again, the difference around 2000 atomic unit. So I think this is very important to consider quantitative discussions. And X is determined as 6,856 atomic unit as the best result, including polarization basis functions at the CCSD parenthesis T with finite field perturbation theory level. So, so we propose X as the best result here, and wrote a paper in molecular physics. And this is the result of radium oxide, radium F+, mercury O, mercury F+ system. And so from compared to Dirac-Fock and CCSD, we can see that X value is decreased around 10 to 20%. So electron correlation is important for quantitative discussions. And this is interesting, but so the trend of decreasing or increasing are different in radium or mercury, and it's not like intuition. So average calculations are very important. Here, I wanted to compare mercury atom and mercury F+ molecular systems, because EDM of mercury atom is the lowest EDM at present, like this. And when we compare molecular and atomic systems, we have to compare X value of molecules and X value of atomic times external electric field used in the experiments. Then the molecular case, this is 10 power minus 9th. Atomic case, this is 10 power minus 13th. So from here, molecule has 4 order of magnitude larger X than the atomic case. So molecules are advantages in experiments. Then, but by the way, we have some questions about this simple representation of X, because this X only contains the information of electron density at the center of the nucleus. Then we don't know why this is very local. So we revisited the formula itself. Then we refer the Frambone and Ginge's paper in 2002. And here, phi r is an electrostatic potential created by nucleus at position r. And from here, we take Legendre polynomials and only collect the first order in P and T odd term. This becomes like this. And we also want to calculate matrix elements of atomic S function and atomic P functions, Bra and Ket states. This is because only this combination provides a non-zero value of the matrix elements. So we want to compute S and P matrix elements with this phi 1. Then this is described like this in Frambo's paper. Then here, this USP is defined as large and small components, F and G radial functions of S and P functions. Then this USP is integrated in the range of nuclear position. So this would be very close to zero. R is almost close to zero. Then we may take a Maclaurin expansion here. Then this Maclaurin expansion, if we stop at k equal 1, then this integration becomes like this, and it's equivalent to the x value defined previously. And using this approximation, this matrix element can be factorized as defined here, and times x, and this s is called the shift moment. But stop at k equal 1 may be very rough estimation, even this USP is local value. Then actually Frambo and Ginges discussed the higher order terms in 2002 paper also, and defined another dipole moment, local dipole moment L, which contains higher Maclaurin expansion coefficients inside of the L, and use X definition. And their strategy, this PK, Maclaurin expansion coefficients, are taken from analytical expression of the wave function using a finite nucleus model, so not numerically solved for multi-electronic systems. But about this integration, these terms are actually easily calculated if we use Gaussian basis set functions to represent molecular wave functions. The Gaussian basis function is reasonable because it is a solution of hydrogen for the Dirac equations based on a finite nucleus model. So we checked the reliability on Gaussian basis functions here. So we calculated thorium neutral atoms and plot the large and small radial functions of 6s and 6p orbitals. And in Gaussian basis functions, we use 34 number of basis sets for both S and P functions. And compared to the results obtained by the graph 2K, which corresponds to numerical basis sets results, so basis set limits. So we can see that, so this R 1.5 times 10 power minus 4th, this is a range of nuclear size. Then we can see that inside the nucleus, this electronic radial function is well described by the Gaussian functions. So we can confirm Gaussian is okay. So then we can integrate this USP using Gaussian basis sets. Then this would be very simple, and this is actually exact formula. And if we take Maclaurin expansion here, then the first term is actually corresponds to the conventional representation X. And so, for this matrix element, there are several terms. So we have to divide into two terms. First one is electronic term 1, which consists of just integration of USP. Then second term, it contains our vector representation, and In this integration, it's a little bit complicated, but we have, again, analytical formula, and it contains error function here. And similarly, if we take Maclaurin expansion, then the first term corresponds to the conventional representation. And hereafter, we only talk about electronic term 2, because this term is more complicated than the electronic term 1. And actually, we know what is the exact expression at the Gaussian basis set, but we have to integrate these functions using nucleon coordinate and using nucleus density. So I think after obtaining electronic term, we have to calculate nuclear physics problem. And so for this, another integrations, probably if we have error functions, it's a little bit time-consuming or complex process. So in this sense, this electronic term, this is exact, but maybe it can be represented by the polynomial expressions.
Almost a couple of more minutes before you can wind up.
Okay, thank you.
Yep, yep.
Okay. So we calculated 5 molecules, thallium fluoride and the other 4 molecules at the Dirac-Coulomb-Hartree-Fock method using UTChem program. And we plot the electronic term 2 of HOMO. HOMO is highest occupied molecular orbital in the region of nuclear radius from 0 to 2.10⁻⁴ atomic unit. You can see this is Fermi distribution nuclear model and for thallium. And so 2.0 10⁻⁴ is this level. Then we show the exact expression using Gaussian basis functions. And also we show the polynomial expressions using Maclaurin expansions. And also we take an Taylor expansions. This is performed at the nuclear radius R obtained from experiment, so around here. And also we take polynomial expressions using least squared fitting methods over the 0 to 2 times 10⁻⁴ range. So here is the results of a Maclaurin expansion in thallium fluoride system. And the black curve is exact representation. And the Maclaurin 2 is only the first term that is equal to the conventional X representation. And the Maclaurin 10 is, we have higher order terms at Maclaurin expansion. Then we can see that the R region R is close to 0. The agreement is okay, but the R is larger case, so around the skin region, this difference is very large. And even we include the higher order terms, that it's very difficult to express, more difficult to express in the R is larger case. And okay, then we take Taylor expansion at nuclear radius. Then the agreement is okay around here, but the deviation becomes larger in R equals 0 region. Then we take least square fitting over the 0 to 2, this region. Then fitting to the R square term is a little bit slight, still deviated. But if we take false polynomials, then the agreement is getting very well. And we have very similar results of in radium oxide. So Maclaurin shows very bad trends, and radium F plus, HGO, HGF plus. So, but in any case, the fitting to fourth order gives very nice results. So here's a conclusion. The electronic term for the shift moment may not be described by the Maclaurin or Taylor expansion because the nucleus has a finite size. And the least square fitting to the first order polynomials provides better representation to the exact electronic term. So we will extend this concept for the electron correlation calculation in future. Thank you very much for your kind attention.
Yeah, so thank you very much, Dr. Abe-san. So actually I'm taking over because Dr. Pai has lost the power connection. We have this problem in India. Okay, so there are a couple of questions. One is from Simran itself, the moderator. So she is asking, is this question worth taking up that what is the difference between electric dipole and electric dipole moment? So maybe she's she's an undergraduate student, so you can answer to her. So,
okay.
Abe-san, are you able to hear me?
Yeah. Okay, yeah, I just want to see the question. Is it in
So
YouTube?
she's asking, what is the difference between electric dipole and electric dipole moment? Oh yeah, okay. We have the, we have now Dr.
Sorry,
Pai.
you continue. Just
No, it's
continue.
okay. Go ahead, please. You take
No,
over.
because I've not got that question, so you please ask.
Okay.
Our failed here
So,
for us.
okay, Simran, maybe I'll explain. This is very simple question, so we'll discuss that later. So, okay, is there any other question from YouTube? Let me see. Okay, so okay. I think it was from YouTube.
Okay.
Okay. Maybe you can answer. It is from YouTube. So it's again some student has asked this.
So electric dipole. So electric dipole moment. I don't get this meaning, but generally electric dipole moment is same to electric dipole. But what I see EDM is electric dipole moment existing.
Okay, so okay, let me answer to her question because the undergraduate student. So electric dipole is just it's an operator. If you just calculate the expectation value, we call it a electric dipole moment. So what you understand about electric dipole, the definition that also validates here. The definition ER, and you calculate the expectation value of that operator and gives you electric dipole moment. Yeah.
I see. Okay, thank you.
Okay. I think we will take a break or.
Yeah, so we'll have break for 15 minutes and come
15
back.
minutes. Thank you, Dr. Abe, for your wonderful talk and all the first half section of this morning section. So we will join back in 15 minutes. That is 11:45 Indian Standard Time.
Shao. Shall I try to upload?
Yeah, you can upload. So let them join later.
I just want to see it whether it's working. For that, what I have to do? I have to
Just share the screen.
share the screen. Okay, let me see. Custom stream service. Share the screen, right?
Yeah, you have teaching problem or what? Why you won't be able to present available in the afternoon?
No, the meeting is there, but I'll be there. Means there is a, because if the time is shifted by some means, then I'll not be there. So I am not able to confirm it, in the sense, but I'll be there. Okay.
Okay.
So let me see that whether I can share this PPT.
Share the screen.
The screen.
So if you go to the bottom, you will see share.
Yeah, I know that.
Arrow kind of thing.
Yeah, that I'm just finding it. Share the screen. Okay. Okay, I have to open the. Okay, I have to zoom. Okay.
And share with your computer microphone.
Yeah, that's true. I have to just give the permission. This is Zoom. Okay, unlock it. First, yes. Actually, we are in all home.
Oh, anyway,
We
this is
can't go
going
to
on
office.
live.
Yeah, that's an advantage.
No. Whatever we are, having conversation, that is also going on live. So.
Sorry. Sorry. Now let me share the screen.
Looks like you have a nice scenery in the background. So you are in which floor?
No. This is window curtain.
Okay.
1 minute. Let me do this first. Where is this? The Zoom I didn't do much. We are using this one. Right. Find share.
Yeah.
Am I able to see?
Yes. Yeah.
That's good.
So you can make it full screen if you like. If you want to, so yeah, there is a cup that if you hit on that, I think it will go to full screen.
Right. That's it. That I. Okay, fine. Thank you. Okay, I'll
Okay,
talk with you later.
After 5.
Okay. Yeah. Fine.
Dr. Pai, are you there? Actually, it seems he tried to reach me. He got some important call or something like that, so he may have to be somewhere else. If he joins back, then we'll start. Otherwise, I'll just start it.
Yeah.
Maybe we can start now and then let other people will join. Okay. So I'll just
Okay, fine.
introduce you. Yeah. So today we have, so this is the continuous of the morning session. So we have Professor Sanjay Majumdar with us. He's from Department of Physics and Astronomy, IIT Kharagpur, India. So he is one of the former students of Professor Das, who's birthday we are celebrating today. So after joining at IIA with Professor Das, after completing his PhD, he was in Germany for some time. Then he came back and joined IIT Madras for 1 year or something like that. Then he moved to IIT Kharagpur, and he has been continuing as professor there for the last 2-3 years. And he will be talking about Faraday instability in Bose-Einstein condensate. So Professor Majumdar, so it's up to you now. It's just so the total time of the talk is 30 minutes. So it includes 25 minutes presentation and 5 minutes question session.
I'm audible?
Yeah, you are audible. Please go ahead.
Fine. Okay. I put my screen being okay. Fine. Good morning. So thank you, Professor Shahu, for a nice introduction. And my screen is seen.
Yes, we can see yours.
Fine. Okay. So, my title of the presentation is Faraday instability in Bose-Einstein condensate. But I'd like to start by thanking the Professor Shahu and the organizers for organizing such a event, which we are celebrating the 65th birthday of Professor Bhanu Das, who is not only my mentor, but he was my, I don't know how to kind of express what kind of effect of his personal life also on me. So, Pranam Bhanuda. I'd like to start by some of the work which I have learned and also inspired by his work. Okay, and this is based on the couple cluster works, and this is a new kind of work which we have started last 5-6 years. It's about the optical vortex beam. I think many of you know that apart from the spin angular momentum of light, which is associated with the polarization of the light, there is another degrees of freedom which is available in the light. That is the orbital angular momentum. And if you can see the screen, that here what happened, the face front of the light actually get twisted. Okay, or what you can see that the pointing vector is no more is along the direction of the propagation. Okay, so if this kind of light interact with the matter, what would happen? In 2006, Bill Phillips group, they have shown that the light which is carrying orbital angular momentum, if you interact with the Bose-Einstein condensate, what would happen that the orbital angular momentum can be transferred to the Bose-Einstein condensate, and physically you will be able to see the rotation in the Bose-Einstein condensate. Now, so depending upon whether you shine the light which is red detuned compared to the transitions, okay, which is available in the atoms of the Bose-Einstein condensate. So that means that if your light is having wavelength more than the resonance wavelength, then what would happen that you'll be able to trap the atom in bright spot of the light. Okay, or if you blue detune the light, and then you will be able to trap the atoms at the center or singular points of the light. Okay, so where actually there is no intensity. So this has been well established, so that orbital angular momentum can be transformed from the light to the matter, but it actually give the macroscopic behavior, like it can have a physical rotation. A question was there that whether we can have the transfer of the orbital angular momentum from light to the electronic part of the electric motion of the atoms which are there either in Bose-Einstein condensate or cold atoms. So there, what is actually seen that these are two photon transition, as it's in that Raman transition kind of things. And what we have shown that it's possible to transfer the orbital angular momentum of light to the atoms only at the level of the quadrupole transition, not at the dipole transition level. Okay, but in the case of molecule, you can have at the level of the dipole transitions. So that was a paper which is 2014 papers which we have discussed from the first principle and derived this conclusion. Next question was that whether this orbital angular momentum which is coming from the light, actually it converts the Bose-Einstein condensate then and then on instantaneous rotation. Question is that how the orbital angular momentum transferred to the matter. So what kind of dynamics actually Bose-Einstein condensate actually feels from the when it interacts with light. So what we showed recently that depending upon the orientation of the vorticity, that means that orbital angular momentum, whether it's +1 or -1, okay. So depending upon that, the behavior or dynamics of the Bose-Einstein condensate actually changes. So here the first row shows that okay, the over a time how those ground state of the density is present. Okay. So what would happen when it we are using here the pulse beam instead of the continuous the pulse beam having the orbital angular momentum. So when you shine this kind of light, what would happen if the orbital angular momentum value is -1? What is seen that the atoms which are at the center of the Bose-Einstein and condensate gets affected by this orbital angular momentum and get a physical kind of values of rotations. Okay, so slowly what we'll see that from the peripheral side of the trap, okay, or condensate, actually atoms get orbital angular momentum. In the case of the OM value is +1, it is opposite. It starts from the peripheral region and then goes to the center. So this is the dynamics which you can see, which we can understand how the orbital angular momentum affects the dynamics of the vorticity of Bose-Einstein condensate. Next question is that okay, we know that when we trap the atoms, we generally uses with the light, and we have tried to find the magic wavelength. This is the wavelength where the differential SES starship goes to 0. So in that wavelength, we generally use that wavelength we use to trap the atom to have this either atomic clock or different kind of cold atom experiment. Now, question is that if you can shine this kind of a optical vortex, what would happen? So what we have shown here in this paper in the PRA 2018, that if we shined the vortex beam, and here we are just talking about Lagrange Gaussian beam, which is one of the example, a famous explicitly used example of vortex beam. If you can focus this beam, okay, what would happen? Here the picture what we are showing, that the transition which is involved with 5s to 4D transition, and we are showing that how depending upon the frequency, the polarization, the dynamic polarity changes. Okay, and for 4Ds and different multiplet of the 4Ds. Okay, and the point where actually they crosses, we say that corresponding frequency and the corresponding wavelengths are magic wavelengths. And here, if you have just circular polarized light, we see that there is not many of them are there. But if we use some light which is having orbital angular momentum, also it is focused. If you focus this, what would happen? Not only that it will affect the polarization, but we may get more number of magic wavelengths. An interesting point is that these magic wavelengths also can be tuned depending upon your focusing angle and orbital angular momentum value. So what actually we can say that you can tune the magic wavelength, and this idea has been taken and used in many experiments nowadays. So the next point, what we are going to say that this dynamic polarity, which we are looking at here, has actually 3 parts. Okay, so which is three parts. That is a scalar part, vector part, and tensor part. And as we know that many of you know that to get the vector part, we need spin orbit coupling of light. Okay, so but to get a spin orbit coupling, so apart from the orbital angular momentum of the light, we need to have the light which is polarized. That means it has to be either left or right circular polarized light. And then what would happen? This vector polarity can have the splitting in the hyperfine or fine structure level of magnetic level of the electronic structure. Now here in this paper, actually recent paper, what we are just this paper is submitted in PRL, and Faraday has given a lot of encouragement, and he is asking to prepare it for broader audience. So we are waiting for the final outcome of the edited. But what we are saying that here, that if you just have a linear polarized light, then also you can have the vector polarity if you focus it. Because of the focusing, what would happen that the orbital part actually get twisted, and also that from the vector polarity we will have the different components which is nullified because of the left and right component is nullified. Now because of focusing, they will have different contribution. Ultimately you will get a vector polarity. and which is substantial, as you can see it here. Now, from this tune out wavelength, if you can see that there is a difference in the energy level or polarization contributions at particular wavelengths for different multiplates, that different magnetic level of the multiplates. Okay, and from there, what you can just estimate what will be the fictitious magnetic field. Okay, so here kind of a focusing angle, the 60° which I have used, and for the orbital angular momentum value of 1, using the linear polarizability, what we found out that we can find out that the magnetic field is around 1 Gauss, and which is very substantial, okay, which can be used in many cases. Nowadays, fictitious magnetic field is used in different kind of areas like Bose-Einstein condensate, quantum information. So we have to just put those kind of applications in the paper. So this is the work which actually I want to say that we are motivated from the Professor Bhanudash and his group. We have used their couple cluster code, which actually developed in the Bangalore, and later on we actually modified a little bit with the help of Professor Angam Dilip, who is from PRN itself, and his group, Swami Bhattacharya. And we have also got help from the Professor Bimalandu Dev and my some of the ex-PhD scholars, Anol, Noren, and Pradeep. Kaushik is at present working, he will be submitting. So also during the manuscript preparation, we got help from the Professor Andy Martin of Melbourne, with whom we have some project nowadays. So now let's come back to the main topic of the presentation, that is Faraday instability in Bose-Einstein condensate. So what happened that that Faraday instability, maybe you may know because day-to-day life we see it. Okay, I'll explain also. So this is the paper which is recently accepted, published. Okay, so this is the problem was actually developed by Dilip and Kaushik, and which is programmed by Subroto, who is the little junior in our group. Okay. And during this preparation of the manuscript, we got help from the Simos and Peter from the Germany, and Fanos from the USA. So let's start by just giving some simple picture of the Faraday instability in water. What happens that if you have a water in a container, and if you give the external vibration to the bottom of the container with vertical container, what would happen that apart from the gravitational acceleration, now because of this external force, you will have a modified external accelerations. Okay, so that capital GT is here, that modified one. So if you see it, what would happen that because the kind of oscillation, the periodic oscillation which you are giving to the container, and because of the energy conservation and making the system in equilibrium, the surface of the water or the liquid, whatever you are just looking at, okay, they will have some kind of instability and will have a waveform. So to minimize this energy, what would happen, the wave which they form, that will be subharmonic. That means the kind of the frequency they will have, that will be half of the frequency which actually applied externally. Okay, so this is known as Faraday instability, which is actually Professor Michael Faraday has given in 1813s, and later on actually it has taken different dimension and different applications. Okay, so now what would happen? What would happen that recently Dilip has published a paper. He has done some experiment also, which is published in other places. So that he has published a paper using that cylindrical kind of a free fluid. Okay, so that you have free fluid which is having a cylindrical shape by some means. Okay, and if you are giving kind of sinusoidal perturbation, accelerations from outside. Okay, and consider that here gravity is very weak, so here this kind of capillary kind of a force which is applied. Now, if you use the Navier-Stokes theorems, this is a classical fluid which we are talking, then from the momentum conservation and mass conservation equations, and if you assume that surface of this fluid, okay, will have a deformations due to the external accelerations. So we can just say that from the mean radius, there will be deformations, let's say eta, which is different at different positions. Okay. So if we use that, and what we'll get, because of from the Navier-Stokes theorems, we can find out the Matthews equations, which is a very well-known Matthews equation, and it is for the in-viscid, that is without viscous fluid. Okay, so we can find out the Matthews equation, and which actually this is the Matthews equation which you see it here in terms of the deformation parameter eta. Okay, eta is a little modified here.
It depends that what is the power of this control laser. If this control laser Rabi frequency is very high, then typically the line width is given by this, the Rabi frequency of control divided by this quantity under root B naught.